Hi, welcome to whatever part we're on for the Nixie 2 clock project. I don't know, I've lost track. Wanted to go through the part where we test the real-time clock circuit. I chose the MCP7940. It's a microchip part. It's a real-time clock calendar chip. It's got all the necessary onboard registers. But the important thing is it has battery backup, because I want this Nixie clock to have a battery backup. I don't want to have to reset the time every time I go and unplug it. And it's also an I2C interface. So what I want to do is test out something new that I have here. I'll zoom in on it for you. This is the Bus Pirate. It's made by Dangerous Prototypes. They have a few different versions now. This is kind of an older version. I'm not sure. Let me look here. What version do I have? You would think it would say on it, wouldn't you? Well, it'll end up being in the video later. I'll put it in the comment section of the video. But anyway, for now, just wanted to show you what it looks like. It's a small little board. You can tell compared to my hand there. And we have a few different lights there. We've got power up there, USB, which basically flashes when it's communicating with the USB port. Mode, that will turn on for various different modes that you set. And VRAG, that just basically says that you're sending power off to the circuit under test. So this will actually power the circuit you're communicating with. So basically what the Bus Pirate does is it's a quick prototyping tool. You plug it into your PC and you use basically a standard off-the-shelf terminal program. I like TerraTerm, but there's certainly others out there. You know, HyperTerminal for those that still have that. I don't remember what's the last Windows platform to support HyperTerminal. I don't know, it's gone now. So anyway, I think most people are probably using TerraTerm or something similar. But what this does, it's a prototype device that can quickly get communication protocols up and running. Because you don't want to mess around trying to figure out the communication protocol as you're programming whatever it is that you're programming. In this case, the Nixie tube clock. Now, I'm pretty well familiar with the MCP7940, so I really wouldn't have to use the Bus Pirate, but seeing as how I have one, I figured I'd go ahead and just give it a try. So let's say you're using a chip in a particular design that you haven't worked with before, and it's fairly complicated, and you're not that familiar with the communication protocol. You know, maybe it's SPI or maybe it's I2C, but the registers are a bit convoluted and you're not that used to it. A good way, first starting point to figure out how that's going to work is to try and use something here like the Bus Pirate, where you can work out the kinks of communicating with the registers and making sure that's working before you start worrying about whether or not you can actually get the communication port itself working. So if you can get the register part out of the way, figure out all the kinks and bugs, then it's made it that much easier once you've actually built the product and you're going to program it and doing debugging. So yeah, simple device. I just want to point out here we've got USB. That is mini USB, not micro. Seems a bit odd that they would use mini in a newer design like this, but you know, they're still around. You know, just kind of used to micro USB these days. Smaller's better, right? No, I don't know. Anyway, we've got just basically a USB chip here. FTDI or equivalent, I'm not sure exactly what it is. Yep, it is actually an FTDI USB. Then you have a PIC micro. It's a PIC 24FJ64GA004, I think, if memory serves me. And there's some kind of glue logic down here and termination resistor packs, it looks like, over here. No major deal. A couple transistors possibly there. Maybe just for turning the LEDs on, and nothing at all on the back. And then down here you'll notice that we have an actual in-circuit serial programming port, which you can use to directly load custom protocols into the micro, because it's basically just a bootloader program that's in there now. And on the header, one thing that they've done that's really nice, they've labeled things here on the right and the left of the connector. I'll zoom in. Got a few different things there. ADC 3.3 volts, ground 5 volts, pull up, MISO, MOSI, you know, various different things for communication protocols. So anyway, let's get this thing connected, this bad mamma jamma, and see what it can do. I'm going to go ahead and plug in our ribbon cable connector for connecting up to our circuit. One thing that's really annoying about this, they were not thinking. This is the correct way that ribbon cable goes in there. Yes, it goes that way. Well, it should go that way. It doesn't make any sense. Why would they do that? I don't know. That's how they designed it. And then it just has nice little connectors on the end that can, ooh, sorry about that, that can just plug into wires or little terminals. And what I'm going to do is I'm going to plug it into my breadboard. So let me do that. One thing I almost forgot to point out, Dangerous Prototypes does have this little handy guide that you can print out from their website, and it has a list of various communication protocols and essentially what wiring that you're going to want to use for that particular protocol. So we're going to be using I2C, so we're going to see that SDA is going to be gray and SCL will be purple. So if we come over here, we can see our wire colors here. You can see it here too, but really it's not all that helpful. This is what I really think is nice, where you can see exactly what goes where, and you know, I think it becomes pretty obvious where things go. So for example, we're going to use 5 volts, so orange will go to 5 volts, brown will go to ground. We're going to be using the pull-ups internally, because I2C is going to need a pull-up on the lines. They are open collector, and it says also that we're going to be needing to use gray and purple. So we've got purple. It's not clock. It's actually well, it is clock. SCL is clock, and gray, which would be MOSI. But that obviously that's SPI. But in this instance, it is telling us to use the gray for SDA. So let me get it connected, and we'll see what this thing can do. Okay, so at this point, if I've done everything correctly, everything should be connected. We've got our pull-up voltage there, just going to VCC. We've got violet, which is SCL, gray, which is SDA, so these are our two I2C. And then we have brown, which is ground, and orange, which is our 5 volts. You can see I have my chip set up there. You can barely see down in here. There's a little watch crystal, and our 2 load capacitors. And I've also got a green LED and dropping resistor there, just to test the multifunction output pin. This particular chip is supposed to have a 1 Hertz output directly out of the chip that I think I'd like to use for like flashing colons between the numbers on the clock. I think it'd be interesting to have that. So that's one thing. Hopefully we can send a command to tell it to flash that. So let's go ahead. I'll move over to the screen capture now. Yes, I'm going to use real screen capture. Yay! It's about time. Anyhow, let me move over and do that, and it will be instantaneous in your world. Be right back. Alright, obviously this is not proper screen capture, but before you judge me, I tried. Believe me, I put a lot of time into trying to get the screen capture working, but it just was not having it. Obnoxious. This is a Windows Vista machine. It is not my best computer. That could be the issue, but I just couldn't be bothered to get the other one out. Anyhow, I have Terra Term, if I could talk here, open right now. I'm going to go and open the serial port here, so click serial. I've got it plugged in, but it doesn't appear to be recognizing it. Let me unplug it and plug it back in. No? Let me close it, reopen it. Try again. Serial. Always technical issues, you know? Just never works first go. Hold on. Well, that was obnoxious. I had to go and download the FTDI drivers from the FTDI website and install those, and then it didn't work happily with Windows Vista, so I had to find a legacy driver, and, well, yeah, it's been about 30 minutes that I spent messing around with this thing trying to get it going. Not looking good for the Bus Pirate so far. But, you know, it could just be the fact that I'm using Windows Vista, so I'm not going to say that it's a bad product just yet. Could just be me and my Windows Vista machine. Anyhow, I've got it connected there. You can see we're on COM8. Oh, I can see myself now. Hello. See if I can get a better angle here and get some of my reflection out of there. Anyway, so we just have a blinking cursor at this point. And that may actually be because I don't have my serial port set up correctly. So let me bring that up here. See, we've got COM8, that's correct. Baud rate 9600. I'm not sure about that. Let me look. Okay, so I just looked it up. It is not 9600. That seemed rather slow to me for USB anyway. The answer is 115.200. But it is 8 data bits, no parity, 1 stop bit, no flow control. So we'll hit OK. And now I should be able to say question mark, enter. Aha! We have communication. It's working. Beautiful. I like that. Let me see if I get this in frame better here. Sorry. I know. Before you say anything about the screen capture or lack of screen capture and land-based me, well, I don't care. I don't care if you think that I'm a bad person because I didn't screen capture. Anyhow, we have, it says high Z right now in the bottom with a blinking cursor, but you can see it gave us all kinds of information here. Protocol interaction information, general information. But the first thing that we want to do is we want to set the mode. So if you come up here, you see there's a M, little lowercase m there, which says change mode. So what we'll do is we'll hit M, enter, and I have to scroll down again because I didn't screen capture. I know. Okay, so we want I2C, which is number 4. So we'll hit 4, enter, and once again here I am doing this. Set speed. Well, I'm going to say 100 kilohertz is fine. We don't need to go particularly fast, so let's do 3. Enter. And it says ready, I2C. Awesome. So another thing that we want to do, if we look back up here, you'll see that we have power supply, that's PSU, power supply unit, off and on. And what we want to do is we want to turn the power supply on. So in order to turn it on, you can see we have lowercase w / uppercase W, which corresponds to off or on. So we want the uppercase W, which corresponds to on, so we'll do Shift W. Sorry, you can't see that. I'm bad at this, I know. Hey, if you don't like it, you don't have to watch the video. W, enter, power supply on. And so what did that do for us? I'm going to go handheld for a second here. On our circuit board, if I can get it to focus, you can see mode. When I did I2C, the mode light came on because our mode was set for I2C, and our power supply light came on there. You can see VREG. And then USB just flashes as necessary whenever you're sending information over. No big deal. And of course our circuit hasn't done anything yet. Okay, let's come back over to the computer. And the next thing that we want to do is enable our pull-up resistors in order to get our I2C working correctly. So in order to do that, you can see right here we've got a lowercase p / uppercase p, kind of like we did with the power supply, and that corresponds to pull-up resistors off / on, so uppercase is on. So what we want to do, come back down here. This is bad, isn't it? This is terrible. Whoop, Shift, P, pull up resistors on. And nothing changed on the actual bus pirate itself. But at this point, we should be good to go. The only thing I'm going to try is, from our menu, I'm not going to go back up there again, but we should be able to type V, enter, and we should be able to see our voltage. Aha, and there it is. There it is. So what it's telling us is what? I don't know. This is interesting information. Oh! Do they do it by pin? Yeah, here. If you look here, pull up, we've got 5 volts, so that's good. We've got 3 volts on our, or 3.3 volts on our 3.3 rail. We're not using it. And we have 5.02 on 5 volts, which is exactly what we want. So there it is. That's our voltages. So now we are going to come to the difficult part where I need to actually program it to communicate and do something. So the first thing that we need to do for this particular chip after reading the data sheet is we need to set it up to use an external crystal, because by default this particular chip is set to use an external clock source. So not necessarily an external crystal, an external clock source coming from, well, wherever it may be coming from. It could be a PLL, it could be from your micro. In this instance I want to use a separate external oscillator crystal because that's what I've got. So we'll set that up. So how do we do that? We're at the I2C prompt. So the first thing we need to do for I2C protocol is we want to send a start bit. In order to do that, we do a left bracket like that. And I don't know if you need to do it or not, but I'm going to add a space just for clarity here. 0B. That just says that we're going to send the value in binary. And the next register that we need to send after our start bit, this 0B, is going to be the address of the actual chip itself, which for I2C comes directly in the datasheet from the manufacturer. Each particular chip gets its own address that only that chip will respond to. So from the datasheet we have 110, 11110. And the 0 at the end just means that we're communicating with it and we're telling it to write, because we want to write to that particular register. If the last bit were a 1, it would say that we're reading from that chip rather than writing to it. So first thing we're going to do is write to it. That's the address. Then the next thing it's looking for is what is the actual on-chip register that you want to talk to. In this particular instance, it's 0x00. The X just means that you're saying it in hexadecimal. I could have written 0B00000000 if I really wanted to, but because it's much easier to type it in hexadecimal, you only need to do 2 digits instead of 8, I opted for that because register is 0. So communicating with register 0, I'm going to do a space. 0B, this next one's in binary, and now we tell it what we want to send to that register. So to recap, we've sent a start bit. Now we send the address of the chip, telling it to write to that address. This tells it to communicate with the particular chip, the real-time clock chip, that we are writing to it with the 0. The 0x00 is the address on the chip that we want to write to, and now we put in the value that we want to write to that address. So that's 10000000, because it's that 7th bit, the most significant bit of that 0 register on the chip that sets the external crystal. And then we're going to finish that off with a stop bit, which is a write bracket like that. So let me hit enter. If we've done everything right, that should set the external crystal. And what it says is we've sent a start bit, Awesome, this is great. Start bit, write, DE, we got an acknowledge back, that's good. Write 00, acknowledge, so this was the address for the device as a write. There's the address on the chip, we got an acknowledge, and we wrote our, it shows it in hex, 0x80, which was our 0B1 and 7 zeros. Acknowledged it, and then we sent our stop bit. So, if all is going well, our oscillator should be running right now. We have no way of knowing, but everything that we do from here on out should work. Actually, if I remember right, there should be an oscillator status that we can check for this particular chip. This is a little bit more complicated, but it should be a start bit, space, that address again, 0B110111110. So again, that's the address of the chip. We're writing to it. We want to write to register 0x03 this time. We're going to send a repeated start because that's what the datasheet asks for. So we just sent another start bit. Now we need to tell it that we want to write to this address. So that's the 1101111. So we did the 1 at the end this time instead of a 0. Ah, lab assistant's barking. I'm sure you could hear that. So there we go, that's the address that we want to write to. R, basically in bus pirate communication, R means that we want to read the data back. So we've sent this to the chip saying that we want to read. This is basically telling the bus pirate, hey, read into your internal registers whatever we get back on I2C from the particular chip. So we'll go ahead and hit the stop bit there, and this should give us the status of the oscillator. And there it is. We have, where are we here? There's our start bit, write to DE, just like we had done before, acknowledge, came back from the real-time clock. Then we have 0x03, which is the register we wrote to. We have an acknowledge from that. There's our repeated start bit. 0xDF, which again, that's the address of the chip, but this time we're telling it to read back. Got an acknowledge. We read a 1, and we got a knack back from that, and then a stop bit. And from what I read in the datasheet, the knack is knack, which is also short for no acknowledge, is normal. It's supposed to send that back after a read, so not a problem at all. The 1 tells us that our oscillator is running. That's awesome. So let's try something else now. Let's enable that multifunction pin for 1 Hertz. I want to see that thing actually flash because it's not that interesting just reading registers out of this thing. So here we go. Let's go ahead and send a start bit, space. I'm going to do that old familiar address, 110111110. It's a write. And we're going to do 0x07 this time, which is the on-chip register 7. And to that, we're going to write 0B01000000 and a stop bit. So it's that 6th bit there that we want to actually write that to. Just a 1. And that just says, hey, enable the multifunction pin. So we're going to send it, and it didn't do anything. Why not? Hold on. Alright, we got it. For anybody that was paying attention when I was showing the breadboard before, this should have been really obvious. My resistor was going to the plus side there. But I had nothing going to it. There was nothing powering it, so I just made a little jumper here from our 5 volts for the VCC for the chip over to that, and that powered that and gave us power to run our LED. So there we go. We've got our multifunction pin working. It's supposed to flash at 1 hertz. It seems to me pretty obvious looking at the clock that I actually have here in the lab, and that's not 1 hertz. But that's not terribly surprising. That's probably more a function of this crystal than anything, because we're talking about picofarads worth of load here. What are these capacitors? These are 8 picofarad capacitors to load this crystal, and you know, you can get way more than 8 picofarads of stray capacitance in a breadboard. And anyway, the caps are way back here, and then the crystal you can see is a couple spaces away, so that adds capacitance just being so far away. Of course there's inductance there, but capacitance is our main issue there. So the load capacitance is probably way off, and if you don't have the load capacitance right, well, your crystal will start, and if your load is way off, your crystal won't even start oscillating to begin with. But obviously it was good enough to start, but it's far enough off that it's not running at 1 hertz. It's running at something quite a bit slower, it looks like. So one thing you could do, this particular chip has a degree of calibration in it. We would be able to go in and calibrate the oscillator, compensate for the oscillator to get the right frequency, but you know, with proper circuit board layout, that's not going to be an issue. We can follow up later on and see, once we have our finished design, how far off we are from that ideal frequency that we'd want to see. So anyway, I think I'm going to call it a wrap on that. That's as interesting as this probably gets, but you can see the Bus Pirate made it a whole lot easier to prototype. You know, so yeah, I had to read the datasheet. I had to know what the datasheet said in order to do these things, but that's going to be a whole lot quicker when you don't have to worry about how do you send a start bit, how do you send the address, what about the on-chip registers and those sort of things. It takes care of all of that for you. You don't have to worry. You just send a bracket and it will send a start bit, and it will get your acknowledges and everything back. So you know that your protocol is already working. So all you have to worry about is how to use the actual registers on the chip. Anyway, I hope this was a good introduction. I hope it was interesting. If anybody finds this intriguing and wants to know more about it, I'd be glad to do another video. Not sure what product I'd do it for, but I'd find something. So anyway, like this video if you haven't already done so. Subscribe if you haven't, and we'll catch you next time. See ya.